All right. I can't go backwards on this, but I can go forward. So what we're going to be talking about is delivering meaning in real time at high velocity and massive scale, and how you could construct a system to do that. What I want to really get to, I have some sort of background things to talk about for the first bunch of slides, and then the really good stuff is to get to the code samples that I wanted to show everyone to actually show the integration of these technologies. And the important thing to note in these code samples is the elegance and how simple the integration is. It's very, very nice. So just some brief introductions to some of these and why we're even talking about them. So just briefly about myself, I'm a Spark Cassandra connector committer at DataStax. I've contributed to Akka cluster. I've been using Scala in production for 5 or 6 years now. Been a senior cloud engineer. And I work at DataStax, and DataStax delivers Cassandra as an enterprise platform with many different services, including Spark, integrated on top of it. So this is what we're going to basically talk about very quickly in 30 minutes. What we're trying to do, all of us are trying to do, why these particular technologies, how we can actually try and achieve that, and what snippets of a robust application or implementation could actually look like. And I probably am not going to have any time for questions at the end, but I'm very easy to find on Twitter or GitHub or SlideShare. So let's jump in. So this is a really popular, I've seen this many times, but I really like it. The reason why I have this here is because to implement what we need to implement to derive all the meaning from big data, we need to have a really good sense of handling fault tolerance, because as we know, things happen in production, right? So regardless of the meaning we are all searching for over our vast amounts of data, whether it's in science, finance, technology, energy, or healthcare, there's one thing that we all have to do, and that's how do we actually achieve that. And there are some key strategies that come into play for all of these, which is scalability, partitioning, replication. All of these are really well known, but it's easy to talk about them, and it's a completely other thing to actually execute successfully at scale. So I made a little chart. It's a little bit crazy, but if you think about the meaning of each of these strategies and then look at the technologies that I'm going to talk about in this particular talk, each of these technologies, almost all of them exhibit these strategies, whether separately, on their own, standalone, or by collaborating together. And I'll show you some samples of that. And if you note, there's one technology probably all of us have used before that is not listed here. And this is, had to add this for being in New York. Raise your hand if you've worked with Hadoop in production. Oh, really? Oh, not as many as I thought. I had to add this because, I think Michael touched on this. If you look at a typical word count program in Java with, Hadoop, it's like at least, at a minimum, 30 lines of code. But then you could do these wonderful, elegant one-liners with Scala and Spark. And it's really very, very nice. OK. So at a previous company, I had written our first Scala-based analytics data pipeline. I fully automated it end-to-end with scalding over Hadoop. Scalding is fantastic, but this was for a batch reporting project. And then after that project, I moved back into my typical environment, which is event-based cloud applications. Started a new project where I needed to handle real-time data in the stream. And with completely disparate data models, that's an important aspect of it, from many different data sources. And to me, these requirements were a perfect fit for Spark and Cassandra, which I'd used already, Cassandra, to persist to a lot of aggregated analytics. Okay, and I was right about that, doing Spark over Cassandra. I didn't really read about it. I just thought this would work perfectly. The technologies kind of feed in together, and I'll describe that as we start to look through the Spark Cassandra connector code. But in a similar project that I did later, I found that you need to be able to do both batch and streaming in the same application. And this is a really important point, particularly about Spark streaming, that I don't know if it's the only technology for analytics that lets you do this, but it's one of the very few where you can do both batch and streaming in the same application. So I'm going to also be showing you some samples on how to do that. So Spark really stands out for that. And this is what the stack might actually look like. It's a very simplified stack, but with everything sort of running over Apache Cassandra, Apache Kafka, we have Akka cluster, which Spark uses internally, and then the entire platform of Spark, and then your code running over that. So Spark allows us to easily integrate real-time data from disparate data sources in our event-driven cloud-based applications. We can run our computations, both streaming and batch, and in something like our Akka actors, which I'm going to show you. It's very robust, fault-tolerant parallelization, which is really, really helpful to abstract all of that away for you. We also gain exactly once messaging guarantees. TD is going to talk later today in depth about Spark streaming, so I really don't want to go into it. But how many people are using or familiar with Spark streaming? Okay. I'm not going to get descriptive about it, but oops, I skipped my Cassandra slide, and now I can't go back. So that was a really quick one on Cassandra, but we're going to talk more about that in a second. Cassandra is massively scalable, high-performant, always-on, masterless, cross-data center platform database. It's NoSQL, a fully distributed architecture, customizable replication, high performance, and very easy operations. Kafka, high-throughput distributed messaging system, handles massive data load, provides back pressure in our systems to handle the floods and spikes of incoming data volume, which in my experience is very important, and distribution and partitioning across nodes in the cluster. And then Akka. Akka is based for the JVM, unfortunately for any Python users, but Cassandra and Spark do work with Python. So Akka is a framework for building scalable, highly concurrent distributed JVM applications. It abstracts any concurrency issues that you need completely. Very easy encapsulation for design by leveraging the actor model. And this is kind of going to be our playground for everything in the next 20 minutes of the talk. So taking some of the biggest database challenges in the world is what we've been doing with Apache Cassandra. Netflix, for example, uses Cassandra with Database Enterprise platform. They do 1 trillion transactions a day through Cassandra over thousands of nodes over many, many data centers. It's linearly scalable. Complete data centers can go offline and your systems are still up. I know there's someone here from the Weather Channel. Weather Channel uses it as well. It's very easy to use operationally, which I've experienced that myself. It's very nice. And Apple uses it extensively. So this is my 10 things about Cassandra slide. I haven't actually counted it, but 10 things about Cassandra. There's no concept of master or read replicas. We test 1,000 node clusters every day, and we keep those clusters up for days at a time. We do that with our Spark testing as well. It has structured and semi-structured and unstructured dynamic data. Backups take less than a second. Adding a column to a table will take the same time with 1 row or a billion rows. New nodes automatically add themselves to the cluster, so we have elastic scaling natively. DataStax drivers discover new nodes automatically as they come up. You'll never have to shard again. For some people, that's a really nice point. Every write is durable. Replication across multiple data centers provides lower latency. You can survive regional outages. It's a perfect platform for mission-critical applications, and it's the largest production deployment has over 75,000 nodes. So if a Cassandra node fails or gets overloaded during a read, queries are retried to a different node, and nodes down does not equal database down, as it does for many databases. You can have a data center go down, and that does not mean any of your operations around that go down. Your applications can still run in other data centers because we cross data centers. So you can lose over half of your cluster and still be online and fine. And I don't really know why I added that one, because I think I had a talking point, but I just thought it was funny. Oh, I know why, because we specialize in working with big data use cases. I have to blame my teammate for that. Cassandra, some of the use cases for it are with financial data, for security, sensor data, scientific data. Also, data storage for machine learning and Internet of Things. Very useful for that. So it has, for its availability model, is based on the Amazon Dynamo paper. It's distributed in masterless. The data model is based on Google's Big Table. It's network topology aware, and it does multi-data center replication. And then Spark with Cassandra, a Spark node can transparently communicate across data centers. Faster feedback loops for things like fraud detection and content recommendation. And there's no clunky layer between analytics and a data store so this allows one to couple with the other very elegantly. I'm going to go through these slides pretty quickly because I want to really get to the code to show you. With regard to fault tolerance, Cassandra has a masterless architecture, so all the nodes are the same. So you can have half your data center or entire data centers go down, and if a node in a cluster goes down, one or more copies of that node's data is still available on other machines in the cluster. And then replication can be configured to work across one data center or many data centers and multiple cloud availability zones. It leverages things like gossip and consensus. It uses the Paxos algorithm for a consensus protocol. And as an engineer, working with it is now incredibly easy. Since we've come out with CQL, it looks just like SQL. So for engineers, it's very typical syntax that we're used to. You can use CQL with many different languages, and it uses Paxos for locking. It's incredibly expressive, primarily because of how Cassandra itself is designed, but you can do your regular table structure, but then do things like with clustering order by. So what this is going to do, and I'm going to talk about this in depth shortly, but this, for example, with time series data, allows all of my writes to be written in from most recent. So it's in order. So that way when I have my reads and my writes, when I want to pull the data back out, it's all in order. So I don't need to have Spark, for example, be doing any sorting for me, because the thing we want to avoid is any extra work. So we just delegate and let Cassandra do that wherever possible. OK, so the Spark Cassandra connector, this is an open source project on GitHub. We're able to read and write data to and from Cassandra between Spark. We can integrate between in Spark streaming Kafka. You can asynchronously read data from the Kafka stream, do some computations through Spark, and then write anything to Cassandra in the stream. Excellent for time series work. There's also a Java API, but the rest of it is really written in Scala. One of the things that we like to talk about is the importance of trying to leverage data locality when you're working between Spark and Cassandra, because the way that the Spark Cassandra connector works is because Cassandra is network topology aware, it's able to feed, if you have them co-located, the nodes, then you can feed the partition information that Cassandra is aware of to the Spark RDDs and its partitioning, And by virtue of them working together, you can really take advantage of greater speed in your computations. So getting started using it, the basic things, oh, I passed a slide, that's too bad. Well, there's only two things that you have to do to just start using the connector in your Spark code. It's a very simple import, which uses sort of the pimp your library pattern. So you just do either the Spark context or the Spark streaming context import in the connector, and then you can start reading and writing to Cassandra. So this just shows the basic layout of it, where we have the Spark context, our usual work, anything that is going to take any kind of data collection, and then you can just call save to Cassandra, which is exactly like the Spark API has for saving data to Hadoop or to serialized objects, et cetera. And then we just pass in our key space in our table. This is just the most simple example to get us started. Or here I can start doing joins and then save that to Cassandra. I have several different types of joins to show you guys with NoSQL as well. I mean, Spark SQL, so that now you can start doing joins with a NoSQL database. So with Spark SQL, this is just a basic sample of doing a join with Cassandra. So having Spark and Cassandra working together makes both of them, I think, much more powerful. So we're just taking this query data, mapping it right to one of our case classes, saving that data to a particular key space and table. In this Cassandra SQL context, that's part of the Spark Cassandra connector. Here's a sample with working with JSON for Spark SQL. We have our JSON data. I create my Spark SQL context, and then you call the JSON RDD, take that JSON data. I'm transforming it into my custom data type commit stats, and then save that off to a Cassandra table. And then later on, you could see that what I've done is just, I'm using my custom case class, but then when I want to read it back, that call Spark context.Cassandra table, I've used my, my custom data type, my case class, and what it'll do implicitly is map the results back to that. So you get that RDD, resulting RDD, is an RDD of monthly commits. So the connector does all of that for you. So here's an example of working with Spark Streaming, Cassandra, and Kafka. I do a little JSON work there just to show, I think, on the Spark Cassandra connector list, someone had asked me a question of how you could do that, so I just wrote up a little sample, but it's very, very concise. It's incredibly elegant to be able to connect a real-time stream from Kafka, do any number. Here we're just showing one because I want to keep it very simple. But I could be doing any number of computations from that Kafka stream. I could be saving raw data first, and then I could be doing 3 different aggregation computations from that, saving that from Cassandra, or I could be saving some interim data, doing Spark computations, writing some of those results to Cassandra. It's just very easy to work with. This is an example of doing a word count. The reason why I added this slide is because I just wanted to show that with the importance of the right data model with Cassandra really changes everything. And I think I skipped that slide by accident, but it shows the use of Cassandra counters, where if by virtue of using the Cassandra counters in my data model, I don't have to do any kind of reduce by key here. I could just call count by value and then save that word count data to Cassandra. So it lets you sort of shortcut through everything. Basic Twitter sample, where we have our Twitter stream, events coming into the stream, and then here I'm doing count by value in window, so I'm doing some Spark streaming window operations. I transform my data and then save that to Cassandra. So here, what we're looking at so far only is just writing data. So now I'm going to talk a little bit about doing reads. And we're going to get just quickly into the conversion of types and how the connector can help you implicitly do that for you. So here, just by calling Spark context.Cassandra table without anything before the declaration of the key space and table name, It's just going to automatically take that data into a tuple format. So I can call select and aware where I'm doing the pushdown predicate. This is all done server side. None of this is done on the driver or in your application. And the result is it's an RDD, but we've extended it. Obviously, it's a Cassandra RDD of Cassandra rows. But so we can very easily transform that into our own data types. Here I'm doing the same thing. I'm using a streaming context now. Call Cassandra table, and I want the connector to automatically take the data that we're reading out and transform that for me back into my case classes. And that's all I have to do. It will implicitly, assuming that the data structure that you're reading from that table fits exactly, your case class, then the connector will implicitly convert that back for you to your resulting RDD. Working with rows, you can get tuples out of when you read from Cassandra very easily. The thing to remember with tuples is that you do have to call select only because you have to tell Cassandra what order you want the fields in. So you could specify them in any order that you want. But if you just are doing like your own case classes, that's not important. You don't have to do a select unless you actually want to do that. Here's a sample of a key value pair RDD. And then working with columns is very easy too. It's a lot of like the common functions that you see in Spark itself. So I would just call, RDD up first. Working with dates is very easy. I personally like to work with the Yoda Daytime API, so it works with converting that very easily. We can convert specific fields to collections, options. Like if you have a column that might be null, that's perfectly fine. And then we can specify particular rows as well. So I can just call either limit or take. So working with date types is very easy. There's my Yoda sample. And then, if you have formatted date strings, it's very easy to do time slices and time ranges. And user-defined types is something that we just added in the connector. It was recently added in Cassandra 2. So you can see the create type, very different from like your normal table declaration, but that's how you would create it in Cassandra. And then in the code using the connector, you just specify what that mapping would actually look like. Just instruct it on what to do for your custom field in that table, and it handles the rest for you. So you can see I have a type converter, I register it, and then in the resulting read from Cassandra, I have my UDT, my custom data type. And you can easily do this kind of work too with JSON. We have our JSON data, and I create my type. I have a category, I have dimensions, and then I create my table. In the lower right, you can see now I can specify my custom types as field names. Very easy to do. So one of the great things about working with Cassandra as far as use cases is time series. Cassandra is particularly very good with time series data. I think I showed this a little bit earlier, for example, how I set up this primary key where I have this WS ID, for example, is a weather station ID, some kind of ID in your data model. That, when it executes, that's actually because of how I set up my data model, that's going to get me my data locality, which particular node that I want to be querying. So there's little things that you can do in your design working with Spark and Cassandra that can really take advantage of how they can work together. So here Cassandra is automatically sorting by most recent because of how we structured our clustering order by. This is a really good example where we want a record of every event in order in which it happened per URL. So we have a bunch of HTTP events that we're receiving. And so for each URL, I have multiple streams using Spark Streaming. And so I create my receiver stream for my custom HTTP request type, data type, and I'm using the HTTP receiver. And then I just simply do a union on those streams. And because of how I've set up that data model, where I specifically have the primary key of URL, time segment, and the important thing to note here is that TUUID field, that type, time UUID, is a specific type for Cassandra. And that's something that you would always want to be using when working with time series so that you're never overwriting. So the time UUID, what that's doing is protecting from simultaneous events overwriting each other. And the time segment field, I think it's named just segment. No, time segment field. So that's protecting us from running unbounded partitions. So the two of them working together really protects your data from, make sure that it's the most accurate for time series data. And what the time UUID is also giving you is the time of its generation, and it's sorted by timestamp, making them ideal for applications with, if you don't want to have any conflicts, which very often is the case. I've seen a lot of data models that people create, and they don't realize that they're actually overwriting data, so this is pretty important. All right, so now we're finally at the more fun stuff. So I have a weather, it's not a streaming window application, but it's a time series application that you can find online, sort of a reference app called Killer Weather. And the reason that I find it useful as a reference application is because it allows you, it shows you how you can and why you need to integrate both batch and streaming in your compute applications. So this is doing time series because it's taking time-based data that comes in per weather station, hourly weather data, and it's processing that. This is something that's really important when working with Cassandra too. You approach your data model differently than you would with, how much time do I have? Okay. So you approach building your data model very differently than you would with a relational database. You need to, and this is for the distribution and speed, you need to think about what you actually are going to be querying, not just the data model. So like the queries I need to do, I want to get data by weather station. I want to get data for a range of dates and times. And I'm going to skip over this so we can get to the code. So here, for example, is how I'm ingesting my raw data. I have points around my cluster and all of my data centers that are gathering different data sources and processing that and then publishing that to Kafka nodes. So this is an example of how you could do that very easily in an Akka actor. The supervisor strategy in Akka allows you to take, create and implement your own fault-tolerant strategy. This is just a quick sample using some of the Kafka exceptions that you might want different behavior. But the way Akka works is it's hierarchical. So you could have a particular actor isolated to do a certain amount of work, like publish a message or publish several messages to Kafka. And if one or all fail, you might want different behavior. You might want that particular actor to handle that failure. You might want its supervisor actor to handle that failure. You might want some kind of other actor in the hierarchy to handle that. For example, that's what would happen with the escalate. So this is just sending data. It's publishing data to Kafka. This is a sample of an HTTP actor. This is using Akka HTTP and reactive streams. And so all we're doing here is this is receiving HTTP-based data. We're extracting that data and sending it to that Kafka actor through this custom Kafka message envelope. And then what we're doing, this is also a little bit about Akka, is I can then take advantage of the parallelism where I have my, my Kafka publisher. I'm setting it up on a router, and I'm particularly choosing a balancing pool. So what that's going to do is it's going to create 10 instances of that actor, and each of the messages that come in are going to be load balanced to whichever one is waiting for work. And I do the same with the HTTP feed actor. This is a pattern that we do a lot. So this is now on the primary server application that is receiving data through Kafka and Spark streaming and doing the Spark computation. So this is saying, I'm going to create a Kafka stream. I'm processing this data. I'm going to quickly convert it into my own data type, my raw weather data. And then the first thing I want to do is snapshot that out to Cassandra. And then I'm going to do computation. I just want to make sure that I can always rerun that data if any kind of failure happens, so I know that I snapshot it. And then further down the line, I can start doing some more aggregation. So this is, say, an example of a first-level aggregation where I don't need any more data inputs to do this aggregation. It's just what I have right here available. So I can then have all the data come through here, and through a different table, I'm saving this initial type of aggregated data by precipitation aggregate for daily precipitation. And then a second level of aggregation, and this is where the difference between Spark streaming and using regular Spark for batch. 1 minute. So here now, I needed some data to be, some external data points to be able to do further aggregation work on that. And so that's why whenever a get monthly high-low temperature event is received, it goes and computes that through Spark. It receives historic data from Cassandra that we first saved off. We do any of our computation and get our resulting aggregate data from that. You can see here I call collect async because I like to work in futures in asynchronous actors. So I get that back in a future, and then I map that as it comes in into my data type monthly temperature, parse that out, and then I pipe that asynchronously to any requester. And you can see the roadmap. I think I'm out of time, but I have roadmap information on the slides that you can download. If you have any questions, you can find me. And there's resources here that you can find on the slide deck. And that's it.